Hello again. In this video, we are going to define the lower and upper sums of a function with respect to a partition. So let's start with a function. And it's going to turn out we're not going to be able to use any function whatsoever, but a specific type of function, namely a bounded function. So we're going to assume, right, remember what a bounded function means is if I apply f to the domain, that of course gives me some subset of the real numbers, and this needs to be a bounded subset. Okay, so can't get too big, can't get too small. The beauty of having a bounded subset is we know by the axiom of completeness that a supremum and an infimum exists. Okay, so this here is going to tell you that the supremum of the F image and the infimum of the F image exist. And of course, if I take any subset of AB and apply F to it, again, those will still be bounded, and so suprema and infima will exist for the F images of all those subsets. Okay, fine. So I have this bounded function, and let's assume I also have an n partition of AB. Okay, so remember from our partition video, that means I have some increasing sequence from A to B, right? So A is the beginning, B is the end, and then I have some stuff in the middle, and the total number of points, including the A and the B, will be n plus 1. All right, so just a little extra notation here. Let me see here. So we could even write this down, right? So our W, we could write it as A, which is going to be W0, and then W1 and W2, etc. And then we end up with W sub n, which is equal to B. And I'm going to define the sub-intervals that this partition gives by, say, I sub k. So I sub k is going to be the interval that goes from wk minus 1 through wk. Okay, so I can do this for k equal to 1 through n. All right. Okay, fine. So I've broken up my entire interval AB into sub-intervals, all of which are closed intervals. And then I'm going to do one last piece of notation. I'm going to define the length of this interval just to be, well, you just take wk minus wk minus 1. Right? So however long this interval is, that's what I call L of k, and I'll refer to this as the length of the interval ik. All right, so that should be enough here. We can now do our definition. So the W lower sum of the function f equals, all right, so first the notation is going to be L sub f. Okay, this is a little different from the textbook, but I prefer this notation, so that's what I'm going to use. So L is for the lower, f is telling you which function we're talking about, and then it's going to be a function of the partition. So I get the lower sum of f, but if I change the partition, right, I get a different lower sum. Okay, and what is it going to be? Well, I'm going to add up a bunch of stuff. And so, okay, that's why we're going to get a little sum here. And what is the sum going to be over? Well, let's see. I'm going to go from 1 to n, right? So for each one of these intervals, these subintervals, I'm going to get a sum, or a summand. And so how am I going to get it? Well, I'm going to take the infimum of, I'm going to apply f to the interval I sub k. Okay, so I look at the image of f not on the entire interval AB, but just on this subinterval I sub k. And I just ask, what's the smallest value that f can take on, or if it can't really hit a smallest, what's at least the infimum of all those values? And then I'm going to multiply by the length of the interval. Okay, and so that will be my lower sum of f corresponding to the partition W, or for short, the W lower sum of f. All right. Of course, if I have a lower sum, I can also do an upper sum, and it's going to be defined almost exactly the same way. So the W upper sum of f equals, so now I'll use a U for upper, and so the W upper sum of f will again be this sum. K goes from 1 to n, but now I'm going to be taking the supremum of the f image of ik and multiplying it by the length of ik. So I just ask, what's the biggest value, right? Or what at least is a supremum of all the values of f on this interval. Okay? So in your mind, you should be thinking of adding up rectangles, right? This length here, there's my I sub k. I'm just multiplying by the length of the interval. And then that's my base. So what's my height? Well, my height is the smallest value, or the infimum of the values of f. All right, nope, got a little too far over. All right? And when I multiply these two together, right? So this is a base, and this is a height. Okay, so here's my infimum of f of ik. This gives me the area of a rectangle. Yes, of course, it may not actually be an area because this value here could be negative. So this is sort of a signed height. But ignoring that for a moment, right, this is giving you the area of a rectangle, and then I just add them up over all the different i's, right? So here's an ik plus 1. Maybe it's got a little bit different of an infimum. Okay, and I'd add that up. And I can do the same thing with the supremum. Of course, those should be a little bit higher, right? Maybe the supremum is way up here, in which case I'm getting a much bigger area. Supremum over here, again, a much bigger area. Okay, so you give me a partition, and now I can compute the infimum and the supremum on each of the subintervals, multiply by the length of those intervals, add those areas up, and that will give me some lower sum, which you can think of as a lower estimate of the integral of f, and an upper sum, which is like an upper estimate of the integral of f. Okay, so there's our definition. Let's maybe do a couple of examples here. Well, one ought to be enough, I imagine. Okay, so let's go back to this interval from the previous video, 1 to 6. And let's say I have a function f, and it's just going to be the square function. Okay, so f of x will just square everything. Okay, so let's say I have a partition x, which is going to be 1, 2, 4, and 6. Okay, we know that it's going to be not too hard to write down these sums, because instead of it being some k equals 1 to n, how many parts are there? Well, there's 1, 2, 3, right? We count the commas, 1, 2, 3. This is a 3 partition of 1, 6. So there's just going to be 3 summands. So the lower sum is going to be given by, okay, so the first bit, let's see, my I sub 1 is equal to the interval 1 to 2, my I sub 2 is equal to the interval 2 to 4, and my I sub 3 is equal to the interval 4 to 6. So I need to take the infimum of f applied to this first interval. So f applied to 1, 2. Okay, well, I don't do that. Times the length of this interval. All right, well, let's see. The length of I1, well, that's just 2 minus 1 is 1. Now let's do all the interval lengths now. Length of I2, 4 minus 2 is 2. The length of I3, 6 minus 4 is also 2. Okay, so I take this infimum and I'll multiply it by 1. Plus, now I do the infimum of f applied to 2, 4. That's our I2. And I'll multiply it by the length, which is 2. And then finally, I'll take the infimum of f applied to 4, 6. And multiply that by the length of the third interval, which is also 2. Okay, now we know that x squared is an increasing function on the positive reals. So the infimum is always going to occur at the left endpoint. Okay, so this is just a special case. And it's important when you compute these infima and these suprema that you don't always assume that they're going to occur at the boundary. They don't have to, right? They could occur somewhere in the middle. We're just lucky in this case because we know if we're starting in the positive, in fact, we start at 1, that x squared is an increasing function. So the infima will always occur at the left endpoint. So in this case, f of 1 is 1, right? 1 squared is 1. So this is going to equal 1. Over here, the left endpoint is 2. 2 squared is 4. So the infimum is 4. And over here, the left endpoint is 4. 4 squared is 16. So in total, I have 1 plus 8 plus 32, which is equal to 41. So there's my x lower sum for f. All right, now how do we do the upper sum? Well, everything is going to look the same, except everywhere I wrote an INF, I have to write a SUP. So I have the supremum of f of 1, 2. Times, well, it's still the same length, right? Still 1. Plus the supremum of f of 2, 4. Times 2, plus the supremum f of 4, 6. Times 2. Okay, well, the supremum is also going to be easy to compute because, again, x squared is an increasing function, so the supremum is always going to occur on the right endpoint. So over here, the right endpoint is 2. 2 squared is 4. So there's our 4. Over here, the supremum is going to occur at 4. 4 squared is 16. And over here, the supremum occurs at the 6. 6 squared is 36. So in total, we get 4 plus 32 plus 72, which is 108. Okay, and there we go. We've got our x upper sum for f. Now, you notice there's quite a gap between these. 41 is much smaller than 108. So our understanding is that 41 should be a lower estimate, right, of this integral that we want to define, and 108 should be some sort of an upper estimate. Well, there's a pretty big gap between these things. How are we going to improve things? Well, we're going to maybe choose different partitions. Maybe we need to choose a partition that has quite a few numbers here, more than just 3, right? Maybe we need a 50 partition or a 100 partition if we want to get something better. All right. We're going to come back to computing these lower and upper sums and trying to get them to converge to something in the middle later on. But in our next video, we're actually going to prove a relationship between these lower and upper sums, as well as a connection with refinements. Okay, we will see you next time.